Time to look at another exam. This is the third exam for our advanced calculus, or if you like, Calc 2/Math 166 course, which means that we're going to be dealing with a very serious topic. That's right, it's time for sequences and series. Woohoo! We're going to have fun. We've got 7 questions ahead, but of course, as always, if we want the points, well, we better make sure that we put our name on it. And we're ready to begin. Number 1. The sequence AN is defined recursively by, we have a start, A1 is a half, and then we have a rule. So that's what it means by recursive. In other words, to figure out the term I want, I look at what comes before. And so it says, if I want a term, I can find it by taking 4 times the previous term squared, divide by 3 plus the previous term. All right, part A. Find A2 and give your answer as an integer or a simplified fraction. Here, simplified fraction says cancel out any common factors. Well, so what do we know? We know what A1 is, and now the rule says if I want A2, what do we do? Well, A2 will be 4 A1 squared over 3 plus A1. In other words, we took the formula and plugged in n equals 2. Well, but we know what A1 is. So this is 4 times 1/2 squared over 3 plus 1/2. Now, a half squared is a fourth, and 4 times a fourth is 1. So that's good. That simplifies the top. Now, we've got to keep simplifying, right? Because it says give your answer as an integer or a simplified fraction. What about 3 plus a half? Well, 3 is 6 halves, and 6 halves plus 1/2 gives us 7 halves. Or, if we flip, that would make it 2 sevenths. And there we go. That's very simplified. Nothing more that we could do to make that fraction nicer. On to part B. And this one's worth 8 points. Okay, so we have to think a lot here. Assuming that our sequence of the A sub n is decreasing and convergent, find its limit. All right, so what is that saying? Well, it means our numbers are going down, and it's going to approach something. Okay, well, what can we do? Well, let's suppose that AN converges to L. We know it's converging, so it converges to something. Let's give it a name. All right, well, what can we do from our recurrence to find what L is? Well, we can start and say, hey, let's look at AN equals 4 AN minus 1 squared over 3 plus AN minus 1. Well, now say, hey, that left side, it's going to L. What about the right side? Well, if A sub n goes to L, what does A sub n minus 1 do? It's not L minus 1. It's also getting close to L. So essentially it's just saying, for really big numbers, I'm close to L. So if I'm a really big number or a really big number minus 1, still a really big number. So we get L is 4 times L squared over 3 plus L. Well, okay, now our goal is, what's L? We can multiply 3 times L plus L squared, so moving that across, is equal to 4L squared. All right, well, we can move things around. Let's move everything over to, say, that side. All right, well, then we get that 0 is 3L squared minus 3L, or that's 3L times L minus 1. All right, so what does that tell us? Well, we don't need to worry about the 3. It tells us 2 candidates. 0 or 1. Now, it's not both. It has to be one of those two, 0 or 1. Now, how do we figure it out? Well, we can do a little bit of reasoning here and say, all right, what's happening? Well, we know we're going down. That's good. We also know we're starting at a half. Now, we know we're going down, by the way, because of this word decreasing. And we know we're starting at a half. So if I have a half and I'm going down, can I get to 0? Yeah, of course. Can I get to 1? No. To get to 1, I'd have to go up at some point, but we're not. So it's like, oh, okay. So it has to be 0. Can't be 1. And it has to be 0 because we start at 1/2 and we decrease. And there we go. That's the idea. All right, good. Well, now we have our sequence done. And remember, a sequence is essentially a series of numbers. And now we'll probably turn and do something where we start adding. All right, well, let's see what the next problem has for us. Number 2. The following infinite series each converge. Find their sums, and each final answer should be an integer or a single simplified fraction. So we got to clean it up once we're done. All right, well, when we're trying to find series, and we know they converge, there's more or less 3 candidates. Geometric, telescoping, or it's a really nice series. In other words, it's something that comes from a Taylor series. So usually we're going to be looking for things that are geometric or telescoping. All right, so let's take a look. The first one, we have the sum from 2 to infinity of 3 to the n over 2 to the 2n. Now notice, how do the n's show up? They're upstairs in the exponent. In other words, lots of multiplying going on. And by the way, geometric means multiplying. So there's lots and lots of multiplying. So let's think about this as a geometric sum. In other words, can we rewrite this as something to the nth power? Well, instead of thinking of this as 2 to the 2n, we can think of this as 2 squared to the n. And that's another way to say 4 to the n. All right, so that's the sum, 2 to infinity, of 3 to the n over 4 to the n, which is a sum, n equals 2 to infinity of 3/4 to the n. All right, nice, nice. Now, how do you add a geometric sum? And the answer is a geometric sum, which looks like some number plus number times r plus number r squared plus ... is equal to a over 1 minus r. So there's 2 parts. There's the a part, and really you should think of the a, this is the first term. Then there's the r part, and the r is what you're multiplying by. So if we can figure out what's the first term and what we multiply by at each step, then we have our sum. Life is good. Well, okay, so let's start. What's the first term? Well, we are starting our sum at 2. So our first term would be 3/4 squared. All right, plug in n equals 2. Now, what do we multiply by? Well, at every stage, we're multiplying by 3/4 because it's 3/4 to the n. So that's our r to the n. So 1 minus 3/4. All right, well, we found the sum. So we're going to get a lot of points, but we haven't simplified, so we're not going to get all the points, not yet. But that's all right, we have time. 3/4 squared would be 9/16. 1 minus 3/4, well, that's 1/4. And now you can flip and say, okay, this is the same as 9 over 16 times 4 over 1. And, okay, well, 4 and 16 have a common factor, so we end up with 9 over 4. And there we go. That's our answer, 9/4, 2.25. Or if we're engineering students, 2.2500. And that way we have more accuracy, right? So, all right, there we go. So part B, we've done geometric, probably going to go to telescoping, but also definitely is not going to be geometric because we don't see things raised to the nth power. So what can we do? Well, one of the things is we've seen problems like this before and say, you know, let's see if we can pull it apart. Now, the goal of telescoping is we're going to have something minus something. And what we want is to have the things that we're subtracting be very similar so we get cancellation. And that's why it telescopes, right? It's this collapsing. That's what the telescoping is. So, well, let's first rewrite it. So, okay, do some partial fractions. Who doesn't love a good partial fraction? Okay, so 3 over n plus 1 times n plus 2. It's going to be something over n plus 1 plus something over n plus 2. And now we just have to figure out what a and b are. So clear your denominators. Once you have the form, multiply through so there's no denominator. 3 is a times n plus 2 plus b times n plus 1, right? Because we completely cleared out the denominator there. The n plus 1's cancel, leaving an n plus 2. The n plus 2's cancel, leaving n plus 1. And make good choices. Yes, always make good choices. So n equals -1 would lead us to 3 equals a times 1 and b times 0. Ah, a equals 3. How about -2? Well, that would be 3. That goes away, a times 0. Minus 2 plus 1 is -1. So minus b. Or we could say b is -3. Okay, now all this work in this partial fractions, which we're doing off here to the side, is all about rewriting our sum. So let's rewrite our sum. Move this up so we have some space. Well, that says that this is really the sum, n equals 1 to infinity, of, now a is 3, so 3 over n plus 1 and minus 3 over n plus 2. All right, now these are very similar to each other. They're just slightly offset, right? This has n plus 1 versus n plus 2. And that slightly offset together with the minus is what's going to allow us to get cancellation. Now, one quick note to make. The good news is these terms are going to 0. If they weren't going to 0, we could still talk about telescoping, but we'd have to be slightly careful about the ends. But since the terms go to 0, then that says, look, it's all at the beginning. So let's start by writing down the first few terms and see the behavior. We're starting at 1. So we will have 3 over 2 minus 3 over 3. So this is the n equals 1. Plus, now n equals 2. 3 over 3 minus 3 over 4. All right, what about the next one? Well, it's going to be n equals 3 now. 3 over 4, because now 3 plus 1 is 4, minus 3 over 5, and dot, dot, dot. Dot, dot, dot is mathematical shorthand for saying, and the pattern continues. Well, we see that actually we get cancellation pretty quickly, right? The 3 over 3's cancel. which is good. The 3 over 4s will cancel, which is good, and so forth and so on. And it keeps going and going and going. What doesn't cancel? What doesn't collapse? Well, the term at the start, and you might say the term at the end. Now that's why I wanted to check what's happening to these terms. Technically what you do is you look at partial sums, and you say, okay, so you have the beginning term, your 3 over 2, and your end term, which is like 3 over n plus 2. That's going away. So the punchline is it's 3 over 2. Now, do we need to simplify this? And the answer is no, it's already simple. It's a beautiful looking fraction. And so we're done. We're done. So be on the lookout. Geometric and telescoping. Those are two of the most common ways that you'll actually be able to say, hey, I can add these series up. Number 3, using the direct comparison test and justifying each step, determine the convergence of the following series. All right, so direct comparison test says, suppose you have non-negative terms, and everything here is non-negative because you squared the cosine. So that's non-negative. So everything's non-negative. And it says, all right, if you can bound it above by something which converges, then you also converge. If you bound it below by something which diverges, you also diverge. So now the trick is to say, which way are we bounding, above or below? Because we're asked to determine convergence. So it's one of those things where you kind of like have to know the answer before you begin. But that's okay. We can know the answer before we begin because we can just reason out really quickly. What do we say? Well, the top is basically n. The cosine squared n, that's not very big. It's never bigger than 1. So the top is n, and then the bottom, well, if we ignore the n squared, because that's the smaller part. So now I'm thinking limit comparison when I'm trying to make up my mind. What we see is it looks like n cubed. So n over n cubed is n squared downstairs. P series, which converges. Okay, so we think it converges. All right, so maybe we should put a little thought bubble here. So by thinking about it, we've now reasoned that yes, this converges. But we've now got to justify it. So our goal is to say, okay, let's bound it. So we're thinking of this, these are our terms a, n. So to do the direct comparison test, what do we want? We want to find some terms bn so that there's two things. One, an is less than or equal to bn, and 2, the sum of bn converges. Now I'm not going to worry too much about start and stop because it's always the start. It's never the start actually. It's never the start. It's always the infinity part. Well, okay, we'll say n equals 1, ideally, but if we needed to, we could make it n equals 1,000, whatever. It's the tail. The tail will tell the tale of whether or not you converge. Okay, so let's think about things that are easy to do. We know cosine squared n is between 0 and 1, so let's just get rid of it. So, all right, we'll start with n cosine squared n over 2n cubed plus n squared. That's less than or equal to n over 2n cubed plus n squared. Now, we've got to justify it, right? Because it says justify each step. Okay, so here's our justification. Since cosine squared of n is less than or equal to 1. Okay, so there's our justification for that step. Now, what would we like to do? Well, we'd like to get rid of the n squared. can we do it? Well, let's think about it. If we got rid of the n squared, would the result be something smaller or something larger? So compare without the n squared with the n squared. Which one's larger? Well, the answer is the one without. Now, why is it larger without? Well, because this makes your denominator bigger. Bigger denominator, smaller number. So this is less than or equal to n over 2n cubed. Okay, well, so we'll put a note here. It says, well, here, since we're going this way, we can say smaller denominator leads to bigger number. Because that's what we've done. By removing the n squared, we've made the denominator smaller. And now we say, oh, well, what can we do? We can cancel an n. That's algebra. And we can say, okay, well, that's less than or equal to 1 over 2n squared. Let's get rid of the 2. Why not? That's less than or equal to 1 over n squared. And so this step was algebra. And now this step is, again, same as before, right? Smaller denominator leads to bigger number. N squared is smaller than 2n squared. And so we say, cool. We now have that the original terms are bounded every single time by 1 over n squared. And so our last thing to observe is, let's talk about the sum of 1 over n squared. Do we know that this converges? Because it's not just enough to bound term by term. We have to bound term by something which is nice. Does this converge? And the answer is yes. Why? Because it's a p-series. Now, a p-series is a way of saying 1 over n to a power p. So here we have p, which is equal to 2, which is bigger than 1. 1 is the threshold. So 1 over n diverges, but 1 over n to anything bigger than 1 converges. And so now we can conclude, so by direct comparison test, because we've now done our bounding, life is good. Our original sum, n equals 1 to infinity, n cosine squared of n over 2n cubed plus n squared also converges. What does it converge to? Hopeless. Hopeless. Forget it. You'll never find it. But it's a number, and you can always get a good approximation. And that's all right. We just needed to know yes or no. All right. There we go. Another problem down. We're moving right along. Number 4. All right. So this is one of those fun ones where we just have to circle stuff. So it can be really quick. But be careful. We've seen people circle randomly and get them all wrong. One person one year said, okay, I'm just going to put all my eggs in the basket, and they went all the way down and said, okay, I'm just going to pick a column because something's got to be there, right? Well, that time there was nothing in that column, and they got 0 still. So don't try to game the system. Just learn to answer the question, right? That's perhaps the best way to game the system. All right, so what do we need to do? We need to decide whether the given sum, and there's 5 of them, whether they are absolute, conditional, or divergent. So let's think about what's going on. Let's start with our first sum. We see alternating sign. That's good news. And when you see alternating sign, you can say, does the terms go to 0? And if they do, then you have the alternating convergence test, which means convergent. So it's not divergent. Okay, so you've ruled something out. Ruling something out is actually not bad. It improves your odds. But now is it conditional or absolute? If you got rid of the minus 1 to the n, it looked like 1 over n plus 2. Now the plus 2 is not important. It looks like 1 over n. And that is the harmonic sum which diverges. So in other words, that minus 1 to the n is important. And if minus 1 to the n is important, then that means that we are conditional. All right, so conditional. Cool. All right, next one. Cosine n pi. Now secretly, by the way, cosine n pi is a way to hide a minus 1 to the n. So it's minus 1 to the n over n squared. Again, we see alternating sign. We see the denominator getting big, so the whole terms go to 0. It converges. Do we need to have the alternating sign? Drop the numerator. You get 1 over n squared. P series, n equals 2. That's convergent. So you don't even need the alternating sign. So that tells us absolute. Cool. All right. Now, the next one. We have lots of plus signs. When we see lots of plus signs, and we don't have to be careful, we say, okay, ignore the small terms. And we say, okay, so we're going to ignore everything that's not an n squared term upstairs and not an n squared term downstairs, because those are small. You say, okay, by the way, what are we doing right now? We're doing limit comparison. Limit comparison, get rid of the noise. The noise is the small stuff. So the terms look like 2n squared over 3n squared, also known as 2/3. Now, does the sum of 2/3 converge? No, no hope at all. Because what's happening is that the terms themselves aren't going to 0. If the terms go to 0, hopeless. It has to diverge. So that's a basic divergence test, if you will. All right. Now, the next one. Minus 1 to the n over n to the 10th, 10 to the n. Now, this is one of those things when you just say, what wins between polynomial versus exponential? And the answer is exponential just wins in a landslide. It's super good. So you always want to bet on exponential growth. So, okay, so what does that mean? Well, the denominator is going to a huge number far faster than the numerator, and so it's going to be absolutely convergent. Now, you can do more sophisticated things. You can talk about things like a root test, which says, okay, ignore the minus 1, and downstairs, the root of 10 to the n, we're talking nth root of 10 to the n, is 10. Then upstairs, it's the nth root of n, which is going to 1. So this is absolutely convergent. But this is one of those things where it's just a matter of make sure you understand how things grow. And once you know how things grow, you'll know the behavior. Last one. Okay, we're adding upstairs n plus 1, downstairs n cubed plus 2n. We're taking the square root. I see noise. So whenever I see plus stuff, I always say, look, ignore the lower order stuff. So I'm going to ignore all of the stuff that I've just marked here. So covering that up, you really have n over n cubed, which is really 1 over n squared, inside a square root, which means this 1 over n. This is behaving like 1 over n. What do we know about the sum of 1 over n? That sum is divergent. So by limit comparison test with harmonic, it's diverging. And we're done. We didn't write down notes because we knew things. Now we could have written down stuff, but we wouldn't get any extra points. But there we go. Conditional, absolute, divergent, absolute, divergent. Number 5. We're asked to find the interval of convergence, not the radius. We will find the radius, by the way. When it says not the radius, it means it's not just the radius. So the difference between the interval of convergence versus the radius of convergence means you need to worry about endpoints, and you kind of got to pay attention to where your center is. All right, so we're finding our interval for the power series below. Carefully justify your reasoning and say the names of the tests you use. So when you're finding the interval of convergence, you always start with either the ratio test or the root test. Now, when do you do the ratio test? Mainly you pull out the ratio test if you see factorials involved. When you don't see factorials, it's almost always root test. We don't see factorials, we're going for root. So we say, okay, so we're going to think of the following. If we think of this as just one big thing, right? So this is our, we'll call it a sub n. So applying our root test, we get the following. So root test, we're going to take our limit as n goes to infinity, absolute value of a sub n to the 1 over nth power. Well, all right, that's the limit as n goes to infinity. When we're taking our absolute value here, well, the downstairs is always positive, and so we can take the nth root of 4 to the n, which leaves us with 4, and here we can push in the absolute value, so it becomes absolute value of x minus 1. Now we take the nth root of 2 to the n, and that gives us 2. And notice there's no n's, so that simply becomes absolute value of x minus 1 squared over 4. Now what's the trick with the root test? Well, the root test says this will absolutely converge when this is less than 1. It will diverge when it's bigger than 1. When it equals 1, we don't know. And so that's when we have to do endpoints. But before we get to that, let's finish up here. So we know we absolutely converge for right now when absolute value of x minus 1 squared is less than 4, or take a square root of both sides, absolute value of x minus 1 is less than 2. So what is this saying? Well, I want to compare where I am in relationship to 1. Because when you see an absolute value, it's really saying, how do two things compare? What's the distance between them? And we want to say the distance from x and 1. So picture-wise, we have our number line. We have 1. And now we're going to go out 2 in each direction. So that gets us up to 3 and down to minus 1. We know for sure in between minus 1 and 3, we're all good. Outside, we're all bad. It's not going to work, which leaves us with 2 points. So now we're going to test endpoints. So in some sense, the first step is pretty quick, right? Apply a root test or ratio test, and we're going to get everything except the endpoints. Now we do the endpoints one at a time. So testing endpoints. 2 endpoints, so we have to do this twice. So let's start with x equals negative 1. Now, by the way, endpoints should be kind of on the edge. And so you can't apply a ratio test or a root test to do endpoints. And so if you're like, oh man, this endpoint, this is converging super nicely by a root test, something's wrong with your endpoint. Okay, so at negative 1. So minus 1 minus 1 is minus 2. So this becomes the sum, n equals 1 to infinity, minus 2 to the 2n over 4 to the n. Well, that's the sum 1 to infinity, minus 2 to the 2n. You can think of it as minus 2 squared to the n, so it's 4 to the n over 4 to the n. Well, okay, so that's the sum n equals 1 to infinity of 1. Well, does that sum converge or diverge? Diverges. So that tells us that we are not going to include negative 1. All right, so this should truly be an open circle. Now, what about 3? Endpoints can behave differently, so it's not enough to say, hey, I tested one, so the other one's going to do the same. No, 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 no. You got to check them separately. Sum n equals 1 to infinity. 3 minus 1 is 2. So we're going to have 2 to the 2n over 4 to the n. And now we're going to be like, whoa, deja vu. Yeah, we will have some deja vu. We end up with still 4 to the n over 4 to the n, which is the sum 1 to infinity of 1, which again diverges. And so this other n is also truly an open circle. So now we're ready. What's our interval? Well, our interval is everything between those 2 points. But of course, we want to write that in more mathematical notation. So our interval will be -1 less than x less than 3. Or if you like using your parentheses, you could say -1 comma 3 with parentheses. That means not including the endpoints. And that's it. That's the problem. Wow, we're going quick here. Nice. It's fun when the test goes fast. But okay. Classic kind of problem. Interval of convergence or radius of convergence. They love these things. So be ready. This is really, you should think ratio and root. Those are going to be your 2 go-tos here. One or the other is going to work. Root is your default. Ratio you pull out for factorial. And if it's interval, grab the endpoints and test them separately. If it's radius, you're basically done almost as soon as you finish the test at the start. Number 6. We're asked to find P4 of x. And this is the Taylor polynomial of order 4. For f of x equals x log of 1 plus x, centered at x equals 0. Now there's 2 strategies that we could go in. One is the literal strategy, which is to say, oh, hey, we can just take enough derivatives and life is good. And one is the build it up strategy. So we'll walk through both of them. So even though it looks like it's going to take a lot of time, if you go by like, my gosh, this problem took like a lot of time. Well, because it's a problem so nice, we're going to do it twice. Okay, so what's the just like full speed ahead? Well, what we can say is that we know how to compute P4 of x. And we say, well, P4 of x, Taylor polynomial, and we're centered at x equals 0. So that would be f of 0 plus f prime of 0 times x. And we're centered at 0, so we're not like x minus 0. It's times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed and f fourth derivative at 0 over 4 factorial x to the 4th. So we have to find these values, plug it in, simplify, we're good to go. So this technique is 1, knowing the rules, and 2, being careful with finding derivatives. Okay, so knowing the rules, I mean know the definition of the Taylor series, and don't forget your factorials. All right, well, here we go. Okay, so what can we say? We have to do lots of derivatives. So we have our x log 1 plus x. So first derivative, well, product rule, derivative of the first is 1 times the second plus the first times the derivative of the second. And now the derivative of 1 plus x inside the log is 1 over 1 plus x times the derivative of the inside, which is 1. Okay, what about second derivative? All right, well, that's 1 over 1 plus x. Oh, that's nice. Now here, what are we going to have? Quotient rule. All right, plus the bottom times the root of the top minus the top times root of the bottom over the bottom term squared. Since we're going to keep taking derivatives, let's clean that up. What we'll see is the plus x and the minus x cancel. So that's going to make it a 1 over 1 plus x squared. And now that's pretty good. Let's do one more thing. Let's make it calculus friendly. 1 plus x to the minus 1, 1 plus x to the minus 2. All right, f triple prime of x, third derivative. So now that it's in this format, minus 1 comes down, 1 plus x to the minus 2. Here, minus 2 comes down, 1 plus x to the minus 3. And our last derivative. Okay, minus 2 comes down, minus 1 times minus 2 makes a plus 2, 1 plus x to the minus 3. Minus 3 comes down, minus 2 times minus 3, plus 6, 1 plus x to the minus 4. All right, so we've taken derivatives. Now we evaluate these at 0, right? It's not that we put in the functions, we put it in the functions at the point where we're centered. So pay attention. They could be sneaky and say, oh, centered around 1. Whoa. No, don't fall for that. Okay, so plug in 0. All right, f of 0, what is that? 0 times log 1. Log 1 is 0, so it's extra 0-y. All right, f prime is 0. What's that? Log of 1 is 0. Then you have here, you have 0 over 1 plus 0. 0. Okay, sure, that's fine, no problem. How about f double prime is 0? Because we ran out of space. Well, here we have 1 over 1 plus 1 over 1 squared. Well, that's 1 plus 1. That makes it 2. How about f triple prime of 0? What's that? Well, 1 to the minus 2 is 1. 1 to minus 3 is 1. So it's really minus 1 minus 2, which makes minus 3. And the fourth derivative at 0? Well, again, 1 plus 0 is 1. 1 to any power. Minus 3 or minus 4 is still 1. So it's 2 plus 6 makes 8. So now we just say, great, plug it in and clean it up, and we're done. So we have our P4 of x is 0 plus 0x, okay, plus 2 over 2 factorial x squared, and then minus 3 over 3 factorial x cubed, and then plus 8 over 4 factorial x to the 4. Well, that would make it x squared. 3 factorial is 6. 3 over 6 is a half. 1/2 x cubed. 4 factorial is 24. 8 over 24 is 1 over 3. So 1/3 x to the 4th. And we're done. Now, I'm not claiming this is the best way, because I don't like to think, this way is best and this way is, is bad. I like to think of it as like, this is a good alternative if you're comfortable. You need to say, look, I'm comfortable with this setup and I'm just ready to go. What's another way we could have approached this problem? Well, we could think about this and saying, it's all about polynomials. And so we have two things multiplying. And in particular, if you look at your function, you say, okay, I have x, that's one thing, and then I have log of 1 plus x. Now here's the thing. I can think about them separately and then combine. Now, the good news about x is it's already polynomial. So I really need to think about log of 1 plus x. Okay, so plan B is to say, let's figure out log of 1 plus x and then times by x. Ah, cool. Now we could be sneaky, but let's not be too sneaky. Let's just go ahead and think about it. So let's temporarily, we'll say g of x, that's log of 1 plus x. And start by taking the derivative. The derivative of log is 1 over 1 plus x. And then we're like, whoa, wait a second. Deja vu. This looks a lot like geometric. In other words, if you think about this as 1 over 1 minus x, that's the sum, 0 to infinity, of minus x to the k power. And you're like, yeah, that's cool. That's really cool, actually. Okay, so now that's g prime of x. So how do we turn g of x into a polynomial? Well, we integrate. Okay, so then that says g of x is the integral of the sum, 0 to infinity, of minus x to the k dx, right? Because we took a derivative, so now we've got to go backwards. Well, the nice thing about integration is you can do it term by term. So this will become the sum, k equals 0 to infinity, of, and we're going to break it up as minus 1 to the k, integral x to the k dx, which is our sum, k equals 0 to infinity, minus 1 to the k, x to the k plus 1, over k plus 1, and then plus c. Now, how do you find c? Plug in x equals 0. When we have g of 0, log of 1, 0. So our initial conditions tell us that c equals 0. All right, good. Now, at this point, you're probably thinking, how does this get us our answer? Well, what it tells us is that natural log of 1 plus x starts as, when you plug in 0, you're going to get x to the 1 over 1, which is x. Now plug in 1. What are we going to get? We're going to get a minus, and then we're going to get x squared over 2. All right, plug in 2. We'll be back to a plus, and then we'll have x cubed over 3, and other terms. Now, why do I stop here? Well, looking ahead, we're going to multiply by an x, and I only need to get up to x to the 4th. So that tells us that x times natural log of 1 plus x looks like x squared minus our 1/2 x cubed plus 1/3 x to the 4th plus other stuff. And we say, aha, we got up to x to the 4th. So this part, the Taylor polynomial, is just the first part of the Taylor series. We actually have the whole Taylor series worked out. So here is our P4. So that's our other approach, which is to say we know how to do logs separately, so multiply the two polynomials together, and life is good. All right. That leaves us with one more. One last problem to go. Our last problem, number 7. Find the value of the binomial series coefficient 1/3, choose 3. Your final answer should be an integer or a single simplified fraction. So we got to simplify it after we find it. So how do we go about finding binomial series coefficients? Well, it's actually pretty straightforward once you get the hang of it. So we're looking for 1/3, choose 3. So what we're going to do is downstairs, we're starting with 3, and we're going to multiply till we get to 1. So In particular, notice we start with 3 and we subtract 1 until we get to 1. So there's 3 terms downstairs. I'm going to come back and say that again. Upstairs we have 1/3. And what we want to do is we also want to have 3 terms. So how do we get the next term? Well, we're going to do what we did downstairs. Keep subtracting 1. So 1/3 subtract 1 makes it, oh, I should have given myself more space, minus 2/3. All right, so subtract 1 again. Minus 2/3 subtract 1 makes minus 5/3. And we're done. So we have 3 terms multiplying upstairs, 3 terms multiplying downstairs. Because of that, 3. The first term comes from these pieces, and then we just subtract 1 each time. Okay, so what do we have? Well, we have 1 times minus 2 times minus 5 would make 10 over 3 times 3 times 3 makes 27 all over 3 times 2 times 1 is 6. Well, okay, that's 10 over 27, and then we'll bring this up as a 1 over 6. And now we say, okay, well, can we clean anything up? Well, 10 is 2 times 5. We do have a 2, so we can cancel a 2. That would leave us with a 5 upstairs, and a 27 times 3 downstairs, which is 81. So 5 over 81. All right, so that's part A. That was worth 5 points. We're going to do great. Okay, part B. Find the first 4 non-zero terms of the binomial series expansion of f of x equals the cubed root of 1 minus 1 over x. Okay, so here we go. Let's remind ourselves what's the rule that's being tested here. So the rule that's being tested says the following. 1 plus something to the power alpha is equal to the sum k equals 0 to infinity of our alpha, choose k, times whatever we have to the k power. All right, so that's our generic formula that we have to go off of. And so now the age-old question that we've always thought about. What's in the box? What's in the box? What's in the box? All right, so how do we find that? Well, let's take the thing that we've been asked to find. And so we have this expression. Let's rewrite it to look more like this binomial series. So this is the same as 1, and I'm going to think of this as plus minus 1 over x, all to the cubed root means 1/3 power. Now we're kind of saying like, oh, 1/3. Gotcha. Cool, 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 cool. And so the answer for us is we have alpha is 1/3, and minus 1 over x is what's in the box. So we now get the following. I'm going to switch colors here. This is, according to our handy rule, the sum k equals 0 to infinity of 1/3 choose k times minus 1 over x to the power k. All right, so that's 1/3 choose 0, and then something to the 0 is always 1. Okay, plus 1/3 choose 1, and then we have minus 1 over x to the 1. And then we have 1/3 choose 2, and minus 1 over x to the 2. And plus 1/3 choose 3, minus 1 over x to the 3, dot, dot, dot. I kind of hope that we're there, and I suspect, given what they asked us in part A, it probably will be where we stop. Now, 1/3 choose 0. You might say, well, wait, how do you write down 0 terms? Well, the answer is you just don't write any terms. So what does that mean? Because we're taking multiplication, the multiplication of no terms is 1. If that makes you uncomfortable, just remember the 1/3 choose 0 is always 1. All right, so that's good news for us. So we know what the 1/3 choose 0 is. How about 1/3 choose 1? Well, we can come up here and say, okay, that says we're just going to have 1/3 at the start, 3 at the start, and only have one term on top and bottom. Well, that's 1/3 over 3. Oh, okay. Well, 1/3, whoops, sorry, got that slightly wrong. Let's clean that up. It's not quite that. It's 1/3 upstairs, 1 downstairs, and we stop. So 1/3 over 1, which is 1/3. Here, we're going to get 1/3 minus 2/3. Then downstairs, we're going to have 2 and 1. So we're going to get minus 2 over 9 over 2. So this is going to be minus 1 over 9. And finally, this we can just copy, 5 over 81. All right, so we found our pieces here. Okay, so let's update, and we'll see where we're at. So we now have 1. Here, we're going to have a minus 1/3 times 1 over x. So, well, okay, I can put the x downstairs. Now, the next term, we're going to have 1 over x squared times minus a 9th. So minus 1 over 9x squared. The next term, minus 1 over x cubed. So that's going to become a minus. That's a plus, so the minus. And then we're going to have 5 over 81, and again an x cubed downstairs. And, well, here we go. That's 4 non-zero terms. So we stop, and we're done. Say, great, wonderful, wonderful. All right. And, all right, great. That brings us to the end. Now, I will say on a personal note, it makes me feel a little weird, this problem. And that's because normally when I think of series, I don't like x's downstairs. I like them upstairs. Because I like to think of series as polynomials. However, due to the nature of how this problem is written, at x equals 0, I mean, this problem is nonsensical because it's blowing up. And so we'll give the test writers a pass on this. And just to say, okay, the real thing is, do we recognize binomial series? Do we know how to work with binomial series? And if we do, life is good. All right, well, another test done. Whew. Now, this one is oftentimes one of the more challenging tests, not because the computations are hard, but it's more, you have to think a bit. And it's a little bit less familiar. So make sure you're getting plenty of practice here. The more you practice, the better you'll do. And I know that's always true, but especially this time. All right, well, thank you for joining me, and I hope to see you again. Bye.